As outlined in the introductory lecture, the statistical physics curriculum of Leiden University is based on statistical mechanics. In statistical mechanics, we follow the ideas of Boltzmann, where we start from a microscopic description of a system, then applying statistics and the law of large numbers in order to obtain the macroscopic description of the system. This might be very appropriate in systems where we have a physical description of the microscopic behavior. It is clearly impossible to have such a description for bigger systems, like, for example, a complex machine, even the air co, a heat pump. So the question would be how to derive, in very general terms, the macroscopic behavior of such kind of systems without knowing the microscopic model. But this is what thermodynamics describes. Within the course of Statistical Physics 1, we will have 2 sessions that deal with thermodynamics. And in this very first session, we will discuss the axioms and laws of thermodynamics. We will follow the ideas of J.W. Gibbs, which are based on a few axioms. Now, what is an axiom? You can look this up on Wikipedia or on Britannica. What you will find is that an axiom is a statement that is generally believed to be true, yet without an explicit proof. Mathematics is a strictly axiomatic theory from which you, for example, prove in the semi-ring of natural numbers 1 plus 1 is equal to 2. Gibbs in total defined 6 axioms on which the theory is based. 3 of those are actually used also in statistical mechanics. Yet the 3 others we can prove to be true starting from the statistical mechanics and microscopic view. Axiom 1 states, any isolated macroscopic system will eventually come to a state in which all of its macroscopic properties remain constant. Such states are called equilibrium states. Indeed, this is a definition that we also used in statistical mechanics. The second axiom states the values of all other macroscopic observables in the equilibrium state are determined by a finite number of conserved variables. Also, this axiom we used in the definitions that we made in terms of statistical mechanics. Likewise for the third axiom. The third axiom states, for sufficiently weak external fields, the equilibrium state consists of a finite number of homogeneous components or phases. This axiom just reflects the fact that fields that could influence the state of a system should not vary too much in the volume that we are looking on. Now for the remaining 3 axioms, statistical mechanics actually has a proof. For example, for axiom 4, which is also sometimes called the second law of thermodynamics, which states that there is a function of the macroscopic state of a system called the entropy, S, with the following characteristics. 1. If a system is composed of a number of spatially separated parts, then the entropy of the whole is the sum of the entropies of the parts. And second, the equilibrium state of the system is that state that maximizes the entropy within the constraints of the system and the conservation laws of nature. Now, in earlier lectures, we developed this function S as a measure of the number of states that a system can reside in. And we know entropy is an extensive variable, meaning that the total entropy of a system is equal to the sum of the entropy of its parts, or in terms of the partition function of the total system is just the product of the partition functions of the individual systems. Now, as to the second point, that is described by the law of large numbers. We know for the law of large numbers, where a system is in equilibrium, omega, the partition function, is maximal, meaning that the derivative of omega with respect to any of these observables is equal to 0, and the second derivative is smaller than 0, which means omega is a convex function. Now, since S is just the log of the partition function, both also hold for the entropy. Hence, what Gibbs formulated as an axiom, we actually can prove using Boltzmann's theory. The fifth axiom concerns the behavior of the entropy at its boundaries and says that the derivative of the entropy with respect to any parameter at the boundaries goes to infinity. This axiom will be proved at a later stage when we discuss phase transitions. The sixth and last axiom of thermodynamics, also called the Nernst law or the third law of thermodynamics, states that all minimum energy states have zero entropy. Now, the interpretation of this axiom is given by quantum mechanics. So in quantum mechanics, we know that we can characterize systems by their energy levels, and the lowest energy level is concerned by a single representation. It means omega is 1 and the log of 1 is, and the entropy is 0. Using these 6 axioms, including the proposition of the quantity entropy, Gibbs was able to describe all thermodynamic observations that had been done at that time. And he was actually able to prove the laws of thermodynamics that describe all behavior of the systems. The zeroth law of thermodynamics describes equilibrium. If two thermodynamic systems are each in thermal equilibrium with the third one, then they are in thermal equilibrium with each other. Now we have shown what equilibrium means, namely that the derivatives of the entropy of each subsystem with respect to one observable have to be the same. Hence, if the derivative of S1 with respect to A1 is equal to the derivative of S2 with respect to A2 and of the derivative of S3 with respect to A3, this means that also system 2 and 3 are in thermal equilibrium. The first law of thermodynamics concerns the conservation of energy. If I apply or take out work from a system, its internal energy has to change in the same manner, provided I don't change the entropy. Such processes are called adiabatic processes. Now in this graph you see various processes you can think about in the energy versus volume plot. You can transfer a system from one state to the other, for example, or at a constant temperature. That means dT is equal to 0, and these processes are called isotherms. You could also hold the pressure in the system the same. dP is equal to 0, those are called isobars. Or you can keep the entropy constant, ds equal to 0, and those processes are called adiabatic processes. Hence, the first law of thermodynamics describes the conservation of energy. The second law of thermodynamics, also sometimes called the fourth axiom of thermodynamics, states that the total entropy of an isolated system can never decrease over time. Now, the explanation of this law is that we know in equilibrium the entropy is maximal, which means that the first derivative of the entropy is 0, and the second derivative with respect to any parameter is smaller than 0, meaning S is a convex function. In this figure you see a convex function depending on two variables. Now if we take any cut through this convex function and plot S versus the path that we are taking, the second law of thermodynamics makes predictions what happens to S when I change my system from a state A1 to a state A2. Since I assume that I perform this transformation in a way that the system always stays in equilibrium, it will follow the blue line. Now, since S is convex, this is equivalent saying that the real value of S always is above the direct connection between the points A1 and A2. The system will always follow the higher entropy path. Finally, the third law of thermodynamics also called the Nernst law, describes what happens to S at very low temperatures. Well, at low temperatures, any quantum system will its lowest energy state, of which there's only one realization, hence S is equal to 0. In summary, what we have shown today is that statistical mechanics, as we developed earlier, is able to describe and understand the laws of thermodynamics without further assumptions.